All right, so we've introduced this idea behind chirality in molecules, right? So we've talked about what makes a molecule chiral, right? The definition behind chiral centers. And then if we do have a molecule that has a chiral center, it will most of the time have what is called a non-superimposable mirror image, which we have referred to as an enantiomer. All right, so just as a reminder, enantiomers are these non-superimposable mirror images. Right, and so we've gone about talking about how we can distinguish one from the other, right? So assigning what we call absolute configuration, right? So now we've talked about how to assign R versus S. And so now we're going to go into talking about kind of the way to distinguish, or the way that we have available to us to distinguish between different enantiomers, right? Because a lot of times different enantiomers are going to have different effects overall in the body, right? So for example, at the very beginning of this chapter, we talked about thalidomide, which was that pregnancy drug, right? One enantiomer of that molecule, one version of that molecule did help pregnant mothers in battling morning sickness, but literally just the inversion at one chirality center in that molecule, its enantiomer, had a drastically different effect overall in the mother's body, right? So instead of battling morning sickness, it turned the appendages of their babies into flippers, right? So again, those were two enantiomers of one another. They were non-superimposable mirror images, and they both had very drastically different effects overall in the body, okay? Another good example of this too is how, these enantiomers are different. They're going to behave differently. Comes from this example of carvone, right? So there are two versions of carvone. It has one chirality center in it. So the R version is responsible, this molecule is responsible for the smell of spearmint, right? So it's present in a very large proportion and is responsible for that smell and that taste of spearmint. Whereas its enantiomer, the S version of this molecule, is responsible for the smell and taste of caraway seeds or caraway oil, right? And so caraway is like that little pod. It's kind of got a weird taste to it. I don't really like it that much. It's in Italian sausage quite a bit. They put it in Italian sausage a lot. And it's also kind of a very licorice-y, black licorice type taste, which I'm not a big fan of, right? Again, these guys are stereoisomers, right? They have the same molecular formula. They have the exact same connectivity of atom. It is literally just the fact that they differ in the spatial arrangement about this carbon that can give them very drastically different properties, okay? Now, that's in terms of like pharmacology, of how they're interacting with the body. In terms of physical properties, though, if we look at these two enantiomers, physically, they are not different, right? Both of them have melting points at 25 degrees C. Both of them have boiling points at the exact same temperature. They're both going to behave very, very, very similarly because, again, a lot of these physical properties are determined by the intermolecular forces present in a molecule, not by their arrangement of atoms, right? And so the problem is let's say that I wanted to make a spearmint gum, right? And I wanted to isolate this guy, R carvone, from this guy, S carvone, right? If they have the exact same boiling point, exact same melting point, I can't use things like distillation or crystallization or anything like that to distinguish them. So we're going to go into how we can actually go about distinguishing different enantiomers, okay? The only thing and the only way we're going to really be able to utilize an experimental type technique to distinguish different enantiomers is something called polarimetry. And that's what we're going to talk about at the very beginning of this portion of the lecture. Now, polarimetry is a type of spectroscopy, right? So I'll go ahead and write out spectroscopy here. So spectroscopy. And anytime we deal with spectroscopy, because we're going to very soon move into other spectroscopic techniques that we're going to utilize in organic chemistry, anytime we're dealing with spectroscopy, we're looking at the interaction of matter, which is going to be our different molecules or our different enantiomers that we're dealing with. And so matter's interaction with light, right? So how do these guys interact overall with light? So that's good. Okay, so as a reminder, what is light?
Can either be a wave or a particle.
Wave or particle. If we go even back further, so light in general is a form of what? It's radiation. What type of radiation?
Yeah.
Electromagnetic radiation. So electromagnetic radiation. What is electromagnetic radiation? What does electro mean? What is that trying to indicate? Some words. There's words with elect somewhere in there. Okay, so electromagnetic radiation means that we have oscillating perpendicular electric fields, and it's perpendicular with an oscillating magnetic field. Okay, so all electromagnetic radiation has this oscillating electric field component, right? And it is perpendicular to this oscillating magnetic field component, right? And perpendicular means they are 90 degrees relative to one another, okay? This is the definition of what light is. It's electromagnetic radiation. Okay, so these fields are always oscillating in whatever direction we are shining the light, or whatever direction the light is propagating through space, okay? All right, so that's light, both magnetic and electric field components. Now, does anyone know what polarization is? Because a lot of people actually deal with this on an everyday basis, but they don't really know what they're dealing with. So a lot of times you can get polarized glasses, right? So when you polarize light, what you're actually removing is the magnetic field component. You're only looking at the electric field component, okay? So when we have polarized light, so polarized light, we're only looking at the electric field. The magnetic field is removed, okay? And let's make sure that blue does not work very well. Okay, all right, so that's polarized light, okay? So now, what is plane polarized light, and why do we care necessarily? Okay, so let's imagine that we have a light source, okay? So something over here, which is shining light. The electric field components of this light source have no specific requirement with respect to orientation. So when we draw our nice little electromagnetic radiation, we always have our electric field component moving in one direction, but that's just to simplify the idea behind what electromagnetic radiation is. In reality, when we shine light, we're going to have some of the electric field going this way, some going this way, some going this way. We have all these different orientations with respect to our electric field component. Okay? So the way that we can kind of idealize that is say, okay, in our light source, what's coming out of our light source, we have an electric field component that's moving this way, we have an electric field component that's moving this way, etc. Again, we're propagating through space this way, okay? And again, there's going to be all these different permutations of those electric field components. It's not just 1, 2, 3, it's like an infinite number of orientations, okay? Okay, so again, this is our light source. Light, I like that. That's great, Chelsea. Now, what is polarization, or what is plane polarized light? So when we have plane polarized light, what we have taken is a polarizing filter. So this is a polarizing filter. And what it essentially is just a tiny little slit, right? So we can imagine just this tiny little slit in our polarizing filter. And all this is going to allow through is the orientation of that electric field component that actually fits through the slit, right? So for example, if we have this light moving this way towards our polarizing filter, the only field component or electric field component will be the one that actually matches the slit, which would be this guy. Everyone else gets blocked because it hits the slit, it hits the filter and it doesn't get through, okay? So the light that comes out of our filter here is what we call our plane polarized light. Plane polarized light. Okay? So again, plane polarized light, it has all the other orientations removed except one, and that's what's coming through on the other side of the filter. Yes?
Only the electric field is going through?
Only electric. So in polarization in general, we don't care about that magnetic field. We're only looking at the electric field component, and only the one orientation of the electric field is getting through. Okay, all these other orientations are getting blocked by the filter. Okay, so this is great, right? But what's the purpose? Why do we care about plane polarized light? So the big concept behind this, okay, is that for chiral molecules, or molecules that have enantiomers of one another, each version of the enantiomer rotates plane polarized light. Okay, so enantiomers are chiral objects, so let's say chiral molecules. Chiral molecules will rotate plane polarized light. But now the big kick in this and how we actually can differentiate enantiomers using this plane polarization of light is the fact that one enantiomer will rotate light in one direction of a given magnitude, whereas the other enantiomer will rotate in the opposite direction, the exact same magnitude. Okay, so I'll try to explain what I mean by that. Again, what we're looking at here is the fact that chiral molecules will take this plane polarized light and they will rotate it relative to the way it's coming in. One enantiomer will rotate it one way, whereas the other enantiomer will rotate it the other. And we can measure that rotation at the end of this by using a second filter here and some sort of observer or some sort of thing that can measure the light coming through. What did I call this in this? I called it a detector. Okay, words to me today. Okay, so the idea behind this and the concept behind this is something called polarimetry. Polarimetry. And in theory, you guys should be doing a polarimetry lab very soon.
Yeah.
So we have a polarimeter. We can measure this, and hopefully you guys will be able to actually demonstrate that in real life, okay? Okay, so any type of molecule that actually does rotate plane polarized light, these guys are said to be optically active. So any type of solution that has a molecule in it that actually rotates plane polarized light, these are optically active molecules. Yes?
So, just so I understand it correctly, so when the light passes through, I have my first filter
Yes.
that only allows a specific one source of light to get slid through. I have the plane which is in between. The second filter is to see what direction the light is passing through.
Yeah.
Okay.
And so this is like a brief just like overview of plane polarization and then how we can like measure that. In reality though, what a polarimeter really does is what I'm going to explain on the next slide, how we actually go about measuring this type of stuff, okay? Okay, so what actually happens in polarimetry? Okay, so let's imagine, for example, that we have a molecule. Let's say this molecule is this guy. So we'll say this is bromobutane, okay? And this actually ends up being the R version. So this is R2 bromobutane. And then let's compare that with its enantiomer. How would I draw the enantiomer of this guy, just really quickly without having to draw a mirror image? So whatever this was that was coming out in our R version, in the S version, I just switched the orientation about that group, right? So we have our S to bromobutane, okay? So these guys are chiral molecules, right? We have an enantiomer or we have a chirality center present in this molecule. Because of this, these guys are going to be optically active. They will rotate plane polarized light whenever you shine plane polarized light through them, okay? So now, what's going to actually happen when we go into our little polarimeter? So again, we're going to have a light source, right? And again, that light source is going to have all of these various orientations of electric fields coming out, okay? We're going to shine that light source through our first polarizing filter, right? And so once this guy hits our filter, only the electric field component with the given orientation of the filter is going to come through. Okay, so now we have, again, our plane polarized light. So this is plane polarized. Right, so now let's imagine that we put a solution into our polarimetry tube of the R-bromobutane, right? So imagine that we've got these R-bromobutanes in this polarizing tube that the light is now shining through, okay? When that plane polarized light goes in and interacts with our R2 bromobutane, they're going to actually rotate the plane to which this electric field component is oriented, right? So it came in, pointing directly up and down. As it interacts with these little chiral molecules, that plane is going to be rotated relative to the way it came in, okay? So now, as it goes through, it's going to get rotated more and more and more until it comes out, okay? This is the purpose of the second filter, because what happens at the second filter is we're going to have another filter, right? But we can rotate that filter relative to the first one, right? So we have the ability to move this left or right to a certain angle depending on the orientation of this plane polarized light coming out of our sample, right? So for example, let's say that this filter right now was set to 0 degrees, okay? As this rotated light comes through, it's gonna hit that filter and it's not gonna get through, so we're not gonna observe anything on the other side. But we can rotate this to a certain angle so that we can find wherever this plane is and let the light get through so that we can observe it on the other side. So if I could rotate this and I wanted this to match up with this way, or this guy, what degree-ish would I need to rotate that?
90.
About 90 degrees, right? So if we rotated this 90 degrees to, let's say, the right, then our little plane polarized light would match up with the filter and we could observe it on the other side. That's what we're measuring in polarimetry, is how far do we need to move this so that this rotated light can get through our second filter and we can observe it on the other side, okay? Now, let's say that for our bromobutane, we measured that and we ended up finding that this angle ended up being a minus 23 degrees, right? So let's say we're going through this, we actually have to rotate it this way, minus 23 degrees, and this is what we get for this R2 bromobutane. Now, the big idea behind this is that the enantiomer of this molecule will rotate light exact same magnitude, but opposite direction. So if the R enantiomer rotated it minus 23.1 degrees, then what can I predict that the S enantiomer would do?
The positive 23.
Right. So the S enantiomer we would find would rotate it to the positive direction in the exact same magnitude, 23.1 degrees. Okay, and that's how I can differentiate whether or not I have an R versus an S, is they're going to rotate plane polarized light in equal magnitude, but opposite direction.
Let's just say. And
Yes.
you only rotate it to clockwise?
We can rotate it either way, counter or clockwise. So we can rotate it this way, we'll get a negative degree.
Okay.
We can rotate it this way, we'll get a positive degree. Yes.
Will R always be negative and will S always be a positive degree?
R, no. So we'll talk about that in a second. No. So this is experimental, right? Whether it's rotated to the left or to the right. And I will mention this in a second. This has nothing to do whether or not it's R and S. Absolute configuration and the degree and the sign of rotation do not correlate at all, unfortunately. Okay, so that's the basics. This is what happens in a polarimeter. Again, our sample is in this tube, right? And so it's what is responsible for rotating this light, and that's what we're actually measuring with our second filter and our detector at the end. Okay? Okay, so now, what we're measuring when we measure this guy over here is something called the observed rotation. Okay, so observed rotation is what we actually measure experimentally, and we give it the Greek letter alpha. That's the degree to which we see this rotation of light coming through from our second filter, okay? Now, observed rotation is dependent on a number of different variables. We're going to kind of talk about how we normalize for those different variables. So for example, let's say we have a solution of 1 enantiomer, right? And we put it in our polarimetry tube. The more molecules that are in that solution, the more we're actually going to see rotation of light, right? So one thing that observed rotation depends on is concentration, okay? So we have to take that into account. This observed rotation, the more molecules there are, the more rotation we're going to get. This is directly proportional to concentration. Another experimental variable that depends on how much we actually see rotated is the path length of that polarimetry tube. So the longer that tube that the light goes through, so overall the longer the path length, again, we're going to see an increased degree of observed rotation. So we're going to see this direct proportionality between observed rotation and path length, just like we saw it for observed rotation and concentration. Yes?
So the longer the tube, the more rotation as
The
well.
more rotation you're going to see, the more concentrated the sample, the more rotation you're going to see. Okay, so again, when we are dealing with these enantiomers, though, we would like to be able to compare rotation from one experiment to another. But I've just said, well, it depends on concentration, it depends on path length. So one way that we kind of try to normalize or equalize those things so that we can compare measurements from various experiments is we measure something called the specific rotation. So a specific rotation uses alpha again, but now we talk about alpha in brackets. And what specific rotation is essentially the observed rotation, but now we divide by concentration and path length to essentially try to remove those components so that we can compare these rotations for the same molecule from different experiments. So now in calculating specific rotation, this concentration, which is our little c here, what do we normally measure concentration in?
ML.
Molarity, unfortunately, right? Here, not the case at all, right? So the concentration for specific rotation is measured in terms of grams per milliliter, right? So when we measure concentration, we'll be taking the grams of our optically active molecule, dividing by the mils of solution. And then path length, L, that's what this little L is path length of that polarimetry tube. How do we normally measure lengths? Meters, right? That's a nice standard one. The path length here is actually defined in terms of decimeters, okay? So I don't know why they do this, but they did. So what is a decimeter?
Millimeter and centimeter or
It's in between, yeah, so it's in between millimeter and meter, right? A decimeter is 1/10 of a meter, right? Or usually what you're going to see is 1 decimeter is equal to 10 centimeters, because a lot of times these path lengths are going to be reported in terms of centimeters. You have to convert to decimeters before you can calculate specific rotation. So stupid, I know. It is. It's like, why can't we just set a convention and just use it forever, all of them, right? Why do we have to go to grams per mil? And why do we have to use decimeters? Okay, so one other thing about specific rotation, it depends on the concentration, so we have a means by which we can normalize for that. It depends on the path length. There are other experimental variables that actually affect observed rotation as well. One of them is temperature, right? So temperature is another thing that will affect the observed rotation. And the other is the wavelength of light used. And that's what we're denoting here by this little Greek letter lambda. So this guy is temperature, the big T. And this little lambda here is wavelength. And that's the wavelength of the light source that we're actually shining into this. So to kind of help normalize with respect to that, a lot of times what they'll do is they'll write out in superscript the temperature that you're measuring this at. This tends to be 20 degrees Celsius. And then they will also report the wavelength of light that is used. And frequently with these polarimeters, the light source is a sodium lamp, and we utilize what is called the D line of sodium, which ends up being 598 nanometers. And again, this is referred to as the D line of sodium. And usually what will happen is they'll just write that as D. Okay, so Observed rotation, that's what we actually measure. We can now convert that to specific rotation if we know concentration, if we know path length. And again, these guys are just experimental variables, whatever the temperature is at which you're measuring, and then whatever the wavelength of the light is for the light source of the polarimeter. Okay? Okay, so now we'll go back to our bromobutane, our R-bromobutane versus our S-bromobutane. Okay? I already said that the R enantiomer, it has a specific rotation of minus 23.1. And again, we're denoting specific rotation because we've got alpha in the brackets. What temperature is the specific rotation reported for? 20 degrees Celsius. That's what they're telling you up here. And what was the wavelength of light that they were using? The D line of sodium, which is 598. That's what's going in these superscript and subscript. Okay? So if R rotates at minus 23 degrees, 0.1, then the S enantiomer rotates at positive 23 degree, 0.1. Again, equal magnitude, opposite direction. Now, we do give these guys different names depending on which way they rotate the light, okay? So for a positive rotation, we denote positive as a right hand rotation. And because of that, we call this dextrorotatory, or we will also abbreviate that little lowercase d. So if it's positive rotation, we say that that's right-hand rotation, and we call that dextrorotatory. If, on the other hand, it is negative, we call that left-hand rotation. And we, instead of calling it dextrorotatory, we again go back to our Latin, and we call this levorotatory. And we'll abbreviate that little lowercase l. So that positive rotation versus that negative rotation is dextrorotatory, positive, versus levorotatory, negative. And again, we can denote that with our specific rotation. So this negative 23, our R enantiomer, is that levorotatory, is it dextrorotatory? It's left-hand rotation, it's got the negative, so it's levorotatory. And then for the S enantiomer, what type of rotation is that? It's positive.
That's right.
It's right-handed, so it's dextrorotatory. Okay, so again, coming back to this idea behind RS versus positive negative, or L versus D, they have no correlation with respect to one another. Okay, so if you have an R enantiomer, even though it is negative for this guy, it could be positive for another molecule entirely. Also, even for the same molecule, you can see a change in which way it's being rotated, right? So for example, down here, we have an amino acid. This is aspartic acid, but specifically, it is S-aspartic acid. It has a chirality center in it. At 20 degrees Celsius, aspartic acid rotates the light to the left, so it's negative, right? Same exact molecule, if you heat it up to 100 degrees Celsius, it rotates the molecule to the right, or it rotates the light to the right. Right? So even for the same molecule, you can get different angles with respect to rotation depending on the temperature. Okay, so there is no absolute SR, DL, it's all experimentally determined. Okay, so that is the basics behind polarimetry. So now, we're going to do a problem, and then I'm going to have you guys do a problem which utilizes this, okay? So let's say that we have a solution of sucrose, and sucrose is optically active. It is a chiral molecule. What is sucrose?
Sugar.
It's a sugar, right? So sugars have lots of chirality centers in them. In this problem, we have 0.3 grams of sucrose. It's dissolved in 10 mils of water. We take it, we place it into our little polarimeter, okay? The path length of that polarimeter cell is 10 centimeters. And when we measure the rotation that comes out, the observed rotation, we get a positive 1.99, okay? So from this data, they want us to calculate the specific rotation of this enantiomer of sucrose, or this chiral center with respect to sucrose. Okay, so I'm going to go ahead and write out our little specific rotation equation. So we have specific rotation is equal to our observed rotation divided by concentration times path length. So now, which one of these do I already know that I can already plug into this?
Hold on.
So I know that the observed rotation, alpha, is the positive 1.99. So is this dextro-rotatory or levo-rotatory? This is dextro, it's positive, so it's right-hand rotation. What about concentration? What do I need to do? What does my concentration need to be in units of for specific rotation? Grams per mil. So I do have my grams over here. We have 0.300 grams. What is the volume of the solution? 10 mils. So we'll have to calculate that. It ends up being 0.3 divided by 10, 0.03 grams per mil. Now what about the path length? What does the path length need to be in units of? Decimeters. It has to be decimeters, right? Right now we're in centimeters. So 10 centimeters is 1 decimeter. That relationship was 10 centimeters is equal to 1 decimeter. So for every 10 centimeters, I get 1 decimeter. That gives me a path length of 1 decimeter. So now I can take all of these guys, plug them into my specific rotation equation. So we've got the positive 1.99 divided by 0.03 grams per mil times 1 decimeter. Normally I do this, but I didn't. And I can't do it mentally. Which is? No, okay. 1.99 divided by 0.03, 66. So notice that the positive comes with it, and we're 66.3 for our specific rotation for sucrose. Now what else should I include in my little subscript and superscript?
Oh, the 20.
Right, so this is measured at 20 degrees Celsius. So I need to report that. And it's also using what wavelength? D line of sodium. So we'll just report this as D down here. Okay, so let's go ahead using exact same formula. Exact same concepts. Let's go ahead and try one on our own. Very similar type problem. Now we're dealing with cholesterol, which has 8 chirality centers in it. Dissolved in a ml of water, gets an observed rotation of minus 2.99. I want to know what the specific rotation of this enantiomer of cholesterol is. Okay, so go ahead and give this one a try if you haven't. This is very similar to the one that we just looked at, right? So we have a solution, right? They give us, in a roundabout way, they give us its concentration. They give us the path length of the cuvette, and then they give us the observed rotation, and they're wanting us to calculate the specific rotation at 20 degrees Celsius using the D line of sodium as the wavelength, right? So we just defined our equation for specific rotation, right? So we have alpha in the brackets. Again, this is at 20 and this is at D. Specific rotation is equal to our observed rotation divided by concentration times path length, right? Again, concentration has to be in units of grams per milliliter. Path length has to be in units of decimeters. So The one thing that we are already given at this point is the observed rotation. It is negative, so we can go ahead and define that. We've got alpha as a negative 2.99. Again, negative refers to left-hand rotation, right? So we call this levorotatory, so we can denote that as L. For concentration, again, we need this in units of grams per milliliter. So they tell us that there are 0.095 grams of this divided in 1 milliliter of water, right? So to calculate the concentration, I'm going to take my grams, my mass, I'm going to divide it by the volume of water in milliliters. So this is 1.00 mil. That gives me a 0.095 grams per mil. And then the last thing is the path length. The path length is 10 centimeters. And so for L, this was C, we have 10 centimeters, but we just talked about how we have to convert to decimeters. And the conversion factor here is there are 10 centimeters in every 1 decimeter. So 10 centimeters converts directly to 1 decimeter. Okay, so now we're going to plug those guys in. We've got our observed rotation, we've got our concentration, and we've got our path length. So we've got our specific rotation is equal to this minus 2.99 divided by 0.095 times 1. And so when we calculate that, again, the negative sign follows. So this is still obviously left-hand rotation, levorotatory, but the answer here is a 31.4 degrees. So our specific rotation for this molecule at this temperature using this wavelength of light is minus 31.4 for this enantiomer. Or just this solution. I shouldn't say that, pardon me. Okay, so hopefully that makes sense. And if it doesn't, please make sure to email me and ask me questions. Okay, so when we've been calculating these specific rotations, right? So thus far we've learned how to calculate the specific rotation for an enantiomer given the observed rotation. What we've been calculating these for are things called optically pure. So this is optically pure or enantiomerically pure. So enantiomerically pure. Solutions, essentially, right? So when we're calculating specific rotation, we're doing that with a solution that is only one version of the enantiomer. So it's either only R or only S, okay? So that's what we've been calculating for these specific rotations, are these optically pure or enantiomerically pure solutions. So sometimes we're going to find, especially when we get into things like synthesis and our various reactions, that we're not going to make or we're not going to have just one version of the enantiomer in a solution, right? So frequently we're going to be left with mixtures of both enantiomers in whatever solution we're dealing with, okay? Now, if we have on one kind of end of the spectrum this optically pure or enantiomerically pure solution, and then on the other end of the spectrum, we have, let's say, a 50-50 mixture. So 50% mixture of R, 50% mixture of S. This other end of the spectrum where we have this equal amounts of both enantiomers, this is something called a racemic mixture. So racemic mixture. Anytime you have 50% of one enantiomer and 50% of the other in equal amounts, that's what we call racemic. And I know it looks like racemic, but it's racemic. Okay, so racemic. Yeah. Okay, so with a 50-50 mixture, right, with a racemic mixture, if you imagine, let's say that we have our R version of the enantiomer, and let's say that it rotates light to the right, right? And let's say we have our S version of the enantiomer and it rotates light 50 or to the left, right? Let's say we have equal amounts of molecules rotating the light this way, equal amounts of the molecules rotating the light this way. When you actually see the result of that, you're essentially going to see an observed rotation of 0, right? Essentially, when you do have this racemic mixture, these guys are going to cancel each other out, and you're not going to see any observed rotation, right? So what this results in is a solution that is called optically inactive, optically inactive, right? You're not going to see any observed rotation from a racemic mixture, even though the two enantiomers do have optical activity. They do rotate light in various directions, okay? Now, those are kind of like the two ends of the spectrum, right? Where we have optically pure, you're going to get all this rotation, you're going to be able to calculate the specific rotation, all the way to racemic mixture, where you're not going to get any optical activity because that light rotation is canceled, okay? We're also going to find mixtures that are going to be in the middle, right? So instead of, let's say, having a racemic mixture, a 50-50 mixture, let's say instead that we had a mixture that was 70% of the R enantiomer and 30% of the S enantiomer, okay? So remember that R was this guy, it rotated light to the left, which was negative, and S was this guy, it rotated light to the right, which was positive, okay? Now, this is not racemic, right? Because it's not racemic, there is gonna be optical activity, right? Because we're not equal. From our observed rotation, we have the R enantiomer in what is called enantiomeric excess, okay? So 70% of this guy is the R enantiomer, 30% of this solution is the S enantiomer. The R enantiomer is in excess. And so because of that, the observed rotation from a solution like this would be a negative value, but it's not going to be the full negative value of the specific rotation for the R enantiomer because, again, we don't have an optically pure solution, right? So it's going to be somewhere in between this 23, negative 23.1 and 0 because, again, we're not quite at optically pure, but we're not at racemic either. We can also calculate something called the percent enantiomeric excess, which we abbreviate percent EE, and it's essentially this percent that this enantiomer is in excess over the entire solution, right? So when we have this solution where we have 70% of the R enantiomer and 30% of the S enantiomer, essentially the enantiomeric excess here is 40%, right? R is in excess of S, 40%. To make that a little bit more clear, if we think about the racemic part of this, again, racemic mixtures have equal amounts of S and R. If 30% of this mixture is S, then 30% of the R has to go in to make that racemic mixture. These guys cancel each other, and then the leftover amount of the R, that 40%, is the amount of enantiomeric excess, right? It's the amount that we see when we actually measure the observed rotation. Okay, so with respect to that, it's often very helpful to be able to calculate what percent enantiomeric excess we have in a mixture to see if we have one of the enantiomers dominating over the other. And so the way we're going to do that via the following. So again, we have a solution at this point, right, where we don't know what the percent enantiomeric excess is, but we'd like to know how much of both enantiomers we have, and then who's going to be more abundant, the R or the S, right? So let's say that, again, we're dealing with this bromobutane, right? And again, we know that the R version of the enantiomer is left-handed rotation, and the S version of the enantiomer is right-handed rotation, okay? We have the solution. It's unknown, right? So right now, R versus S is a big question mark, right, overall for both of them. But we take the solution and we go in and we measure the observed rotation, right? So the observed rotation of this solution of the two enantiomers is a positive 4.6, okay? Now, we can take a bunch of stuff just from that observed rotation, right? Number one, the fact that it is a positive value overall, right, tells us which enantiomer is in excess, right? If this is positive and right-hand rotation goes to the S enantiomer, then we know that for this solution, S is in excess. Now, the question is, how much is S in excess, okay? And so to answer that, we're going to use the following equation, which is going to allow us to determine this percent enantiomeric excess, right? So what this is it states that we're going to take the observed rotation, which is our 4.6. Note here that this is the absolute value. So to calculate this, we're not going to utilize the signs, right? Absolute value just means if it's positive or negative, we're just using the magnitude overall. And we're going to divide that by the specific rotation of the pure enantiomer, okay? So for this solution, right, we have an observed rotation of this positive 4.6. So to calculate this percent enantiomeric excess, we're going to take that 4.6, and again, we're going to do the absolute value of it, and we're going to divide it by the specific rotation of the pure enantiomer, which is this guy up here, right, this 23.1. Okay, we're going to take the ratio of those two and we're going to multiply it by 100. And so when we do that, we end up with a percent enantiomeric excess of 80%. And I want to check that because I just want to make sure. 4.6 divided by 23.1 gives us, 20%. That's my bad. That did not seem right. Okay, so this gives us a percent EE, or percent enantiomeric excess, of 20%. Okay, now again, what is that telling us? That is telling us that S is in excess in this solution, and it is in excess 20% over the R. Okay, now again, the entire solution is 100%, right? So if 20% of this is just S by itself, then the remaining 80% is that racemic mixture. And in a racemic mixture, we have equal amounts of both R and S. Again, those guys are canceling each other out, and so we're only seeing that extra or that excess enantiomer 20% of the time, or 20% relative to the pure enantiomer, okay? So if 80% of this is a racemic mixture, that means that 40% of it is R and 40% of it is S, okay? Now, if I told you just to calculate the percent enantiomeric excess and tell me which enantiomer is in excess, then if you said 20% and it's S because of the positive, then that would be fine. But if I want to know what overall percentage is R and S in this solution, then that's going to also take into account the racemic part of it, right? So now, total percentages of the solution for R, we know that R is only that 40% from the racemic mixture that we don't see. But S is both the 40% from the racemic mixture as well as the 20% in excess. So for S, it's the sum of those two. So for S, we have a 60% portion of the solution that is responsible, or that the S enantiomer is responsible for. Okay, so in that previous slide, we had given you this and said, okay, who's in excess and by what percentage? And we had said, it was whatever it was. In this slide, we're actually allowing you to determine these from calculating the percent EE from an observed rotation in an actual experimental setup. Okay, so go ahead and try this one. It's a very similar type question to the one that I just did. So here, this is kind of giving you like a real life type problem where this percent enantiomeric excess and the specific rotation stuff, this observed rotation, is actually utilized, right? So first off, adrenaline, which we utilize in our body. This is also known as epinephrine. Epinephrine that's not how you spell epinephrine. Cool. Is an optically active molecule. It has one chiral center. And so the biologically active version of adrenaline is the R version. And the R version has a specific rotation for that enantiomerically pure solution of a minus 57 or 53 degrees at 25 degrees Celsius. Okay. Now, we have, let's say, a chemist in a lab somewhere who has devised means by which we can synthesize optically pure epinephrine or adrenaline. But there is some chance that maybe there is a trace of the other enantiomer in his synthesized version. So the other enantiomer would be the S, right? He can now take his newly synthesized solution and he can utilize polarimetry and measure the observed rotation to denote, number one, is this optically pure? And if it's not, what is the percent EE, the percent enantiomeric excess, and then from that be able to determine the percentages of both the R and S in his overall reaction mixture, right? So he does this. There's a chance that there's some of the S enantiomer is in there. And so he takes his newly synthesized solution and he measures the observed rotation. And for that observed rotation, he finds it to be minus 45 degrees, right? So again, this should already indicate the fact that he does not have an optically pure sample. There is some amount of the S enantiomer in there. So now what he wants to do is he wants to calculate essentially, again, this percent EE so that he knows how much of the 2 enantiomers he has, okay? So go ahead, try this. You're going to need that equation from the previous slide to calculate this percent enantiomeric excess. And then from that, you should be able to determine what percentages of the R is in this solution and what percentage is the S version of this enantiomer in this solution, okay? So go ahead and pause this, give this a try, and then come back to the answer. Okay, so we'll go ahead and rewrite that equation. So we're going to calculate the percent enantiomeric excess from a solution by taking the absolute value of the observed rotation. So this is observed rotation, and dividing it by the absolute value of the specific rotation. So the rotation for the pure enantiomer. And we're going to multiply that by 100. Okay, so again, our observed rotation was this minus 45 degrees. So we'll go ahead and put in absolute value of minus 45. And the specific rotation for that pure enantiomer was minus 53 degrees, right? So we're going to take those two, again, absolute value, so we don't care about the actual signs, and we're going to multiply, take the ratio and then multiply by 100. So we have 45 divided by 53, multiplied by 100, gives us an enantiomeric excess here. That sucks. Go away. So we have a percent EE of a 85%. All right, so this tells you that our negative enantiomer, which is the R enantiomer, is in excess in this solution 85% of the overall solution, okay? Now, the remaining solution, right, which is the difference between the 100%, all of the solution, and what's in excess, is 15%. And that 15% is essentially that racemic mixture, right? So again, 15% of this overall solution is racemic, which means that 7.5 is R and 7.5 is S, okay? So overall, how good has he been, okay? 85% was R in excess, and then another 5% was R in that racemic mixture. So we can add those two together. We have 85 plus 7.5 gives us a 92.5% of that solution being R, whereas the S is only 7.5% of that solution. So while this is not a optically pure solution of adrenaline, he is getting fairly close. He or she, why do I always do that? I don't know. They are getting fairly close to getting that 100% optically pure R solution, but they are not quite there, right? So this is a good illustration of how something like this would actually be utilized in experimental chemistry.